Thanks, organizer, for the invitation and the introduction. Yeah, it is a pity that due to the visa issue, I cannot attend the conference in person. So I'm delivering my talk online for the event-based vision workshop at CVPR 23rd, which is entitled NeuCAP, Neuromorphic Camera Aided Photography. Here, for the word new, actually it has two meanings. One is for the NEU stands for neuromorphic, or I think people should be aware of this concept after listening to so many wonderful talks in this workshop. And it also has the same pronunciation of the new NEW, which means by integrating the neuromorphic cameras into the conventional photography pipeline, I hope to bring a new experience to the digital photography, or that is really to enhance the traditional photography experience as pipeline. So actually, for the audience on site, can they see the screen of my slides? Yeah. Okay. So actually, we know that the problem-based camera, they are problematic. We have been using it for so many years, but they are slow. They capture a lot of redundant information, and all the information between each adjacent frame, they actually get lost. And also, they have low dynamic range. And if the neuromorphic vision, or particularly the event-based camera, actually can provide a good solution to many problems that we have been encountered during the traditional image pipeline. So people are familiar with the event cameras. It has a lot of advantages in terms of low latency, high dynamic range in terms of for capturing images. Here are a few examples. So I will skip it very quickly because we have been listening so many wonderful talks in the workshop. Very quickly, I also want to mention another type of neuromorphic camera, which is called the spy camera. It works in an integration manner that for a pixel, the light intensity is accumulated. If the accumulated intensity reaches dispatch threshold, a spike is fired and the accumulator is reset. So the visual signal is represented as 0 and 1. Maybe here is a more intuitive example. The first spy camera is designed by the group led by Professor Tiejun Huang in Peking University in 2018 with a special resolution of 100,000 pixels and a temporal resolution of 40K frames per second. So here is we have captured the we have captured the high-speed train in China. Actually, the train is moving at 350 kilometers per hour. We are capturing the data by sitting on the train and watching the other train from the other direction. So actually, the relative speed is 700 kilometers per hour. From the spike raw data, it looks like this. For 1 second, we have 4 PK planes like this, and for each of the planes, for each pixel, we will have either the black or the white pixels. And when we do some integration or the reconstruction method, we can get the image, the clear image of how a fast scene is moving. So comparing to the event-based camera, the spy camera, it has more data has to be recorded. But one of the good thing or the property is that the rich texture information will be captured as well, because when there is no motion, the spike signal is also accumulated or recorded when it reaches the threshold. So actually, in today's talk, I would like to share some of my recent progress in my lab from this direction, that is neuromorphic combining the conventional images. And in our lab, we also do some computational photography research for other type of non-conventional sensors and some interesting problems in computer vision as well. And the website is camera.pku, which is very easy to remember. As the title suggests, we want to introduce our new pipeline with the neuromorphic aided photography. So maybe let's take a look at the conventional ISP or the camera pipeline. People should be very familiar with this one. But when we have in this pipeline, actually there are some bottlenecks or some problems that we encountered when we capture the photo. For example, in front of the lens, due to the conventional design of the lens, we might have the autofocus problem. And due to the limited well capacity and the exposure times, too short, we have the dark images, and too long, we will have the bright or saturated pixels, which is LDR, the low dynamic range image. And also, because usually for a chip CMOS sensor, the signals is read out row by row, we will encounter the rolling shutter artifacts. And there are the noise issue and tone reproduction, which also affect the dynamic range and the frame rate. So let's look at the problem one by one. For the autofocus problem, if we introduce event camera to capture the event focal stack, we will have an all-in-focus image experience. This is a work in this year's CVPR, and we have a poster and probably a courtesy presentation in this workshop as well. So I will briefly introduce a big key idea of how we use event focal stack to conduct the all-in-focus imaging. When we capture the scene using a conventional camera, usually we can only focus on the one depth plane. So there's only one depth, which is in focus. Of course, we can capture multiple images so that we have multiple depths in focus, but usually this is done in a discrete manner. But if we have the event signal and when we rotate, for example, the focus ring of the lens, we will have this kind of all the depth information in focus captured by the event focal stack, because this one moves very fast and it records information, the depth changes with respect to the focus in a continuous manner. This is what we call event focal stack. Of course, if we want to get an all-in-focus image, we can deblur a defocused image, but this is a very highly ill-posed problem. And we can also do image focal stack, but this requires careful operation and consumes a long time and usually collected in a discrete manner. We can also do the focal sweeping by sweeping the focal point in a single exposure. The information is collected from all depths, but the depth information has been lost. So comparing to all these previous solutions, when we do the event focal stack, the intensity, the latent intensity frame changes as the focal point moves. And the events, it actually encodes the logarithm changes of the intensity. And it builds a connection for the latent intensity frames in between. For example, for the epsilon D1 and D2, this kind of continuous information about the focal changes has been recorded in the event stream, also for D2 and D3. That means if we have only one image for without losing generality, let's say we have the ID1, then actually we can, this is a defocused image, can this focus on any unknown focus distance. When we have the event focal stack, we can actually reconstruct the latent image focused at any distance based on the relationship here. So based on this principle, we can develop a pipeline that solves the problem. When we take in a single image plus the event focal stack as input, we can conduct a golden search method for the refocus timestamp, and then for the reconstruction about the image focal stack. And finally, we do the merge to get the all-in-focus image. Let's review the pipeline step by step. For the first step, we do it in a patch-wise manner. Let's say we have n times n patches, and for each patch of the image, we use the golden rate search algorithm to find the moment when it was in focus. And then in the second step, for each refocus timestamp, we develop a very simple neural network called EV-FocusNet to reconstruct the refocused image from the input images plus the event focal stack. This forming an event focal stack as we here for ID1, D2 until DN, we can get the image focal stack. And in the third step, we can predict the merging weights with another simple neural network called EV-MERGENet. Actually, this can also be calculated in using traditional method. We just find that the simple neural network can do this problem in a more noise robust manner. Then, of course, if we do the weighted average according to the calculated weights, we can get an all-in-focus results. We use Blender to render the high frame rate focus with videos by randomly scattering the objects. And then we can use our event simulator to get the event focal stack. This is for our training test. For a training data set. For the testing, we can build a hybrid camera with the event camera and the machine vision camera synchronized by the beam splitter as a real test data. So for the first part of experiment, we would like to test whether our method can effectively remove the autofocus blur. Given an defocused image and event stack, we can see actually for the all-in-focus image, our method is clear on almost everywhere with respect to the ground truth. Well, using single image-based method to remove the autofocus blur is not an easy task. So existing methods might fail in some regions. And this is a result on the real data without ground truth. Yeah, we can see that how our method get clear observations in all these patches. We can also easily do the refocusing given the input event focus stacks, one image focus at an arbitrary distance. Actually, it's blurred everywhere, and we can click on a point to get the refocus. Actually, I like this video very much. So you can feel how the event flows with respect to the changes of the focus distance. Actually, all this kind of useful information along the edges, at which distance it should be clear, has been recorded continuously. This is another example. A third example. This is on the previous two are on synthetic data. This is the result on the real data. This is another example. Okay, so when we solve the problem about the lenses, let's move a little bit further into the camera pipeline. When the well capacity reaches its maximum, usually we get the saturated pixels. This is what we want to solve using the HDR imaging. This is another paper that we presented this year, CVPR, because we know that the human vision is very good at sensing the high dynamic range, and we are living in the real world with very high dynamic range. But when we do the digital photography, traditional method is that we need to merge multi-bracketing images, but this cannot sense moving objects. And if we want to do it in a single image manner, like the inverse tone mapping, this is very ill-posed problem. Of course, we can, with the event-based cameras, we can do the integration from the event to images, but this is still has limited resolution and color appearance representation power. So actually, in CVPR 2020, our group is also the first to propose to build a hybrid camera system that combines conventional cameras and event cameras for HDR images and videos. Our previous solution is like we first integrate or do the reconstruction to get the luminous part of the high dynamic range of the scene. And then, of course, this part is saturated in the conventional images, and we calculate the weight to complement them. And after the fusion, luminous fusion, we add back the color. But this pipeline has some problem is that actually this part is very difficult from the event to the luminous integration. It might introduce some artifacts. So in this work, we try to propose our solution in the shared space, feature space, and to solve the problems to better complement the features from these two modalities of data to enhance the temporal consistency of color appearance of the HDR video. So our motivation is that we want to avoid explicitly reconstructing the event to the intensity first to avoid the artifacts. So this is done to solve this issue. There are two questions that need to be answered. So how to represent events and LDR frames in a shared latent space, and how to extract the common and complementary information for HDR reconstruction. This is achieved by a multi-model representation alignment strategy. First, for the upper branch, we perform the intermodality reconstruction. We still need this kind of conversion, but we put it in this space. And for the bottom branch, we perform the intramodality reconstruction. Actually, this is convert the LDR to the HDR, and the decoder is fixed and it's shared in between these two branches. Then what we need is a shared representation space that complement these two different modalities of data. This is achieved by designing some confidence map, and the fusion is actually in two dimensions. The other one is this kind of a channel-wise. The other one is a spatial-wise. We designed this kind of network architecture and to fit this kind of shared information in the FH to better unify these two different representations. But still, if we look at the videos, we will encounter the flickering artifacts. This is brought by the inconsistent textures, especially from the LDR frames. To solve this problem, we further propose a temporal context encoding to introduce the temporal correlation to further alleviate flickering and reduce the noise. This is also verified on this kind of a hybrid camera system. For the quantitative evaluation using the synthetic data, we will easily observe the large area of saturation in LDR frames, but the event actually has a lot of useful information here. And this is ground truth. This is our result. The number here is HDR VDP score. And this is our comparison to the hybrid method using event camera. And this is a single image based method. And this is our E2VID for using the color event from the Davis 346C camera. Still, you can see this kind of, although by reconstructing the events, we get HDR information, but the color appearance is still not satisfactory. That's why we still need the LDR images with better color appearance. And this one is from another method which merges two exposures. But this one, because they do not provide the linear data, so we cannot calculate the score here. This is evaluation of real data for the image, the hybrid method, single, E2VID. This is another one that tried to denoise and super resolve the images, but this one does not have color information. And this is some qualitative result on the synthetic data for videos. You can see how our result, actually, let's look at it again, has smooth temporal performance as well as the good color appearance. And this is a result on real data. Okay, so when in this part of the camera pipeline, actually we also have this kind of rolling shutter effect. It's because for a cheap CMOS sensor, usually the signal is read out row by row. Actually, this is last year's CVPR work. So I just used 2 minutes to review it very quickly. So this video demonstrates the rolling shutter artifacts. It distorts edges of this moving fan, rotating fan, and also because of the occlusion, the text of CVPR 2020 get lost for this in its rolling shutter image because of this kind of row by row reading out mechanism. But when we have the event information, it actually continuously records a lot of rich temporal information about the hidden or the occluded scenes, and also the correct motion information about the rotating fan. So our idea is, why not we just combine the RS images with the events for both the motion estimation to undistort the edges, and also use the event to image reconstruction to bring back the occluded regions. So at that time, we proposed EV and row, which was the first trial to combine the event signals for correcting the rolling shutter artifacts. After that, I think there are some follow-up works which already have even better performances. And in last year's CVPR, we also built a hybrid camera for a real tested data set. And because we have the event signal, the output video, it is not only global shutter, but also it is high frame rate. Just to quickly look at some results, or you can see comparing to the rolling shutter ones, how the shape of the train get undistorted and how it looks like a high frame rate continuous video. Okay, so the last work I would like to share is also about HDR, and also we try to increase the frame rate at the same time, but this time we are using a spy camera to achieve the 1000 fps HDR and a high frame rate video. Actually, using the traditional frame-based camera to capture HDR video is very challenging. If we use very short exposure time to increase the frame rate, we will encounter a lot of noise. But if you use long exposure, there will be severe motion blur. We can use exposure bracketing by combining the short exposure, the middle exposure, and the long exposure to complement their advantages. This is a good way to do HDR in video domain. But the thing is that there are a lot of time has been wasted for the read time, for the readout, and also for the wait in between the frames. This is actually the key problem of frame-based cameras. But when we have the spy camera or similarly the event camera, actually it captures continuous fast motion in high dynamic range. This is raw data of the spike, this kind of 1010 signals in a fast continuous manner. This has the potential for achieving both the high frame rate HFR and HDR video. And we also build a hybrid system by synchronizing these two types of cameras. And also we use the alternating exposure from the RGB cameras, try to encode both the motion and also the some frames with less noise. And of course, we have the spike trains as input, and hopefully our output is HFR and HDR video. So here is the idea. We have the spike signal. It has a continuous motion information. We can build it, but by simple integration, we can have the spike frame and accurate optical flow information. For the short exposure images, it often contains noise, but we can use the spike frames to warp the middle and long exposure images back to reduce the noise for it. And for the middle exposure, we hope this spike frame can help to do the deblur, which happens to the long exposure as well. Of course, this one has the less noise, but most severe motion blur. So we hope the alternating exposure frames, they can complement each other, guided by the spike frame. Actually, the spike frame and the accurate optical flow information from spike frame, it works as the guidance to interpolate and to warp to align all these frames. So there are 3 steps. So for the first step, we do some pre-processing for the spike frame to estimate the optical flow and to reconstruct the spike frames. And for the RGB frames, we need to deblur it for the middle exposure as a reference and use the spike frames for its calculated optical flow information to as a guidance for the deblur operation for the middle exposure image. And then we warp the adjacent short exposure images to align with the spike guided by the optical flow. This helps to reduce the noise in the short exposure information. And also, because this one has relatively less motion blur, so the color appearance of these 2 different exposed frames will be merged with each other. And the spike frames also helps to interpolate the like in our setup, the middle exposure has 4 times longer time than the short exposure. So it will be interpolated to 4 sharp frames, and the long exposure will be interpolated to 12 sharp frames. But there are still some interval time. This is not recorded in the frame-based camera, but the spike is continuous signal comparing to these discrete frames. So this kind of information, the color appearance between them, is also guided by the optical flow to bring the color information from these frames to the spike frames. And by combining them, we get the high frame rate. There are some other merging modules as well for the refinement of the signals by taking input of the interpolated color frames and spike frames, by using different encoders for feature extraction, and a decoder to reflexively map the deep features back to the current output in the HDR domain. So this is the result. This is on real synthetic data, meaning that this HDR, the RGB are real, and the spikes are synthesized. Here, actually, this is a good example to very intuitive one to demonstrate this is short exposure, middle exposure, long exposure. You can set how the short exposure ones with the correct motion, but this one get blurred, but better color appearance. But this is still like we are playing the slide. It's not continuous motion. But with the spike information encoded and well fused, we will get this kind of smoothed and high frame rate video in the HDR domain. This is on the real data. We can compare with some camera phones commercially available. This is our result. By comparing with those phones commercially available, they cannot sense that fast motion compared to the spike guided video reconstruction. This is another example. And the final comparison is with a conventional high-speed camera, but this one is still frame-based one. In order to achieve high frame like this, in a very short exposure time for each frame, so the color appearance looks a little bit strange, and this is our result. Right. To wrap up, so when we solve all this problem, where we integrate the neuromorphic cameras, it can be a spy camera, it can be an event camera into the conventional ISP or the camera pipeline, We can solve the autofocus problem by capturing event focal stack for out-in-focus imaging. We can also work in a shared latent feature space for HDR video reconstruction to remove the rolling shutter artifacts and do the high frame rate and high definition imaging. So let me go back to the title, the NeuCAP. We have shown some very initial results by integrating the neuromorphic camera that really aid the traditional photography to conquer some bottlenecks, like the frame rate bottleneck, like the low dynamic rate bottleneck. But this is just I hope that this can inspire the future research. And finally, I think there are still great potential, like for either the event camera or the spy camera. The temporal resolution is actually at a microsecond level, but the high-speed video we are recording using this kind of hybrid system still cannot reach that level, meaning there is still some gap between the super photography, and hopefully one day we can put the word here, like the NeuCAP becomes like really the super photography that conquers some, so to bring some invisible or some digital photography experience that can never be experienced using the conventional photography. Yeah, that's pretty much of my talk. Thank you very much.